And we're live. Welcome everybody to Advent of Code 2022 Day 12. You can probably see in the background my Christmas tree is not looking great. I mean the lights broke, so I'll try to fix that for tomorrow. But yeah, sorry about that. Yeah, let's see what Eric has for us today. Let me just get into my coding environment as I always do. I have my files, epic. Right. And I'll have a go at Day 12 and I'll see you after the time lapse. Right, that's part 1 done. Made a bit of a dumb typo error, but I think that's pretty good. Love the graphs, I love graphs so much, so really enjoyed that one. So let's see what part 2 has for us, and I'll see you after the time lapse. Right, that's part 2 done. Yeah, you see I just opened another file there because I thought this code was right, but it might have a long runtime, so I'm just leaving it to run there. And I was gonna check to ensure my code was actually right, or if there were any optimizations to do whilst leaving this running in the background. Yeah, pretty soon after I opened my new file, or the same file to edit it, I got the answer. But anyway, that was a good day. Let's look at the problem statement. Oops. Day 12, hill climbing algorithm. You try contacting the hills using your handheld device, but the river you're following must be too low to get a decent signal. This handheld device is meant to be good and meant to save us, but it just doesn't. You ask the device for a height map of the surrounding area. Your puzzle input. The height map shows the local area from above broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest elevation, B is the next lowest, and so on up until the highest elevation, Z or Z. Yeah, I mean, when I was skimming this, I read height map as heat map. I just read it as heat map the entire time. Until just now, yeah. Oh well. Also included on the height map are marks for your current position, S, and the location that should get the best signal, E. Your current position S has elevation A, and the location that should get the best signal E has elevation Z. You like to reach E, but to save energy, you should do it in as few steps as possible. During each step, you can move exactly one square up, down, left, or right. To avoid needing to get out of your climbing gear, the elevation of your destination square can be at most one higher than the elevation of your current square. That is, if your current elevation is M, you can step up to elevation N, but not to elevation O. This means that the elevation of your destination square can be much lower than the elevation of your current square. For example, blah blah blah. What is the fewest steps required to move from your current position to the location that should get the best signal? Right, yeah. So you kind of read this, and then look, like, you kind of just see this out of the corner of my eye, and I'm thinking, yes, it's a graph. It's a grid graph question today. And I love the graph questions that are based on grids like this. I just really like them. Yeah, I mean, the question itself is pretty short, actually. And, like, you can just ignore the example, because typically with these graph questions, you don't really need the example to understand what it's meant to say. So, like, you can really just read this bit. And yeah, I kind of did. It wasn't too bad. Really not much to include, to be honest. like these two bolded bits are all you need to know in this paragraph. This paragraph, I guess the key bit is kind of reading this. But yeah, I also think that's kind of common sense. I don't know, because obviously best signal is going to be the highest location. And like, because I just saw too low from the corner of my eyes here, I was like, I presume it's meant to be Z. So that's why I just double read this paragraph to ensure I was correct, and I was. But yeah, that was a question. I mean, obviously it's a graph, because you've got like a path. You want to go around the path, figure out where best to go. I'll probably explain that a bit better. So at any given point, you can go to up to 4 other points. So in this example at the start, you can only go to 2 other points. But the idea is, at any given point, you can go to several other points. And you have a destination point, and that's literally a path, right? I'm not going to say it's a tree, because a tree is directed, but this is undirected. But it is like graph, because you have your point. If you think about it, each character in this grid is a node, and each adjacent character has a path between the 2 nodes, between the 2 adjacent nodes. And that is a grid, right? It is a graph. So I mean, this problem is a graph. I guess the idea of recognizing that. But once you do, you can get the code. Right, so this is my code. It's inputting. Yeah, so here I'm just inputting the input, and I'm also splitting into a list. I prefer just to keep things as a list. Obviously, actually, I don't think it would work if you kept it as a string, because you edit it here. Anyway, so I take the input and I turn it into a 2D array essentially, because right now it's just a massive string. So I just turn it into a 2D array. Then this is just where I find where you start and where you end, get the coordinates of those locations, and just like rechange them to A and Z, because your starting position is actually like level A and your ending position is actually level Z. So I'd have to rechange it to them, because that's what they're meant to be. Of course, after I save the coordinates. And then here I do a BFS, breadth first search. That's what all of this code is. Just the classic code. If you ever see me code it before, you definitely know what this is. Yeah, so this is my queue, my deck. And the reason you use a deck as opposed to a list, because this would work as a list. If you change this pop left command to pop 0, it's identical to a list, right? But the reason a deck is better is because when it comes to lists, you only do things in constant time if you do things to the end of the list. Like you can append to the end of the list, you can add, you can remove from the end of the list. And those are all done in really fast and really constant time. But when you use the deck, you get that constant time from both sides of the list. Because it's double-ended queue, deck, double-ended queue, deck. So that's what a deck is useful for, because if you did this with the list, you obviously want to pop from the left or from the start of the list every single time, but that takes a lot of time. And the time it takes to do that increases proportionally to the amount of items on the list. And so with a big graph, probably not with this, because this graph is pretty small, but with a big graph, that would definitely increase your runtime by massive amounts. And that's why deck is important, or useful here, because it ensures you get constant time by popping from the front of the list. Right, and then I just do my classic stuff here, blah blah blah. Here's pretty neat. Here's just where I find out all of the other nodes I can go to next, I guess. So I just go through. So what these 2 for loops do, they just go through each of the 8 adjacent cells. Well, I guess they go through all of the 9 cells surrounding and including your current cell. But obviously you can't move from a current cell to your current cell. You're just moving to the same place. There is no point in doing that. You also can't move corners. So that's what this code does. I mean, to be fair, now that I say that, I do think it does allow you to move to your current cell. I probably should have just fixed that by doing something like this. Yeah, I should have done something like that, but I didn't. But anyway, so what this part of the code does is it ensures you're not going to a corner, because it ensures that either your x coordinate is the same or your y coordinate is the same. And if one of those is the same, then you can never be in a corner, right? Like, you can never move diagonally to your current one. Because if you're moving diagonally, you're changing both your x and y coordinate. Whereas if you move up, down, left, or right, you're always maintaining at least one of those. And that's what this checks. That's why it's good. These two, just check that your coordinates are in bound, right? Because if your coordinates are 0, I mean, I guess 0 is allowed. Yeah, I can. I made loads of logic mistakes here, but seem to work. So I guess that should be greater than or equal to 0. Same for here. Although I guess that doesn't really matter. But yeah, definitely a logic mistake. The idea is your new coordinate has to be within the range of the grid, right? Because even if your new coordinate is like -1, that's technically still allowed in Python, so it's not going to throw an error. But obviously you can't just like jump from top of the grid to the bottom of the grid in this problem statement, right? So that's why you kind of need to check it's within the bounds. And to prevent the Python errors, you also check that it's shorter or smaller than the maximum value it can be, which is len x -1. You just have to check it's shorter so it doesn't throw errors and mess up. So yeah, that's what this if statement does. It basically just checks the coordinates are valid with a few logic errors, but it worked, so we ignore that. And in this line, yeah, you probably notice I do like my one-line if statements. I have tons of them here. But anyway, this line checks if, so the first bit, the if statement, just checks if you're not moving too much of an elevation. And the way I do that is just with odd, turning a character into its like ASCII equivalent number. That's what odd means in Python. And you're just checking to ensure your new coordinate is smaller than or equal to your current one plus 1 in terms of like ASCII value number. I guess another way to do it would be to import ASCII lowercase and I guess use the index of your string of your character, but that's just unnecessary. You can use odd and it's faster. And if so, if it's valid, you check it's all valid at this point, you can just add it to the end of your queue. Boom, that's it. And that is literally my BFS done. And yeah, BFS is important here because it asks for the smallest, lowest number of steps. And the BFS does things in terms of lowest number of steps. Because it says breadth first search. So that means it goes across and then down the tree or the graph. And that means you go across the graph in order of steps. So that means as soon as you encounter an answer, you know that answer is the lowest number of steps because you've accounted for all of the step numbers before that. Hopefully that made sense, but that's the power of BFS. That's why BFS is really good and useful here. But yeah, that was my code. So let's move on to part 2. As you walk up the hill, you suspect that the elves will want to turn this into a hiking trail. The beginning isn't very scenic though, perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start as low as possible, elevation A. The goal is still the square marked E, however, the trail should still be direct, taking the fewest steps to reach this goal. So you'll need to find the shortest path from any square at elevation A to the square marked E. An example: what is the fewest steps required to move from any square with elevation A to the location that should get the best signal? Yeah, so pretty much the same question. I didn't really read any of this. I can't lie, I didn't read any of this. Like, the only part of the question I read, I didn't read any of that. The only part of the question I read was this last bit, and I think that's because it provides enough information to get started. And in reality, it's not saying a whole lot. It's just saying, oh, your starting position is now not S. It's basically anything beginning with A. And yeah, of course, at this point, small modification, but it would also weed out the people who had really inefficient graph algorithms. And also, I guess, test your ability to optimize the graph algorithm you're using. So yeah, most of the code I have is basically the same. What you notice now, instead of starting at S, or like the coordinates to A, which is what I originally did, I now start at any coordinate that begins with A. Like any coordinate that has an A at its like place in the input. So that's what these for loops do. They just go through every possible coordinate, check if it has an A, and if it does, then you run exactly the same algorithm as before. T just stores my answer. Here I'm using 1e99 as my value of T. That just means 1 times 10 to the power of 99. This is just like standard form, just shortened. It's just easier than writing this. I guess writing something like 600 would be fine because based off my previous answer, I knew that the max this answer could be was 534. So I could just write 534 as well. Didn't really think of that, to be honest. But this worked fine. And then what I do here is when I get the answer, I don't print it because I'm now looking for the smallest answer, not just any answer. So I just readjust T to minimum value that I've got so far. The rest of this code's the same. Actually, no, in optimization, because I ran this without this line, and it was a bit slow. I mean, it was slow anyway. It was a bit slow, and just to hopefully speed it up, I checked if the number of steps is greater than what T already is. Because if it's greater, then I don't really care about this entire BFS part. Because if it's greater, then to be honest, a break would probably be faster here instead of a continue. Anyway, it worked. But if it's greater than your current number of steps, then you can ignore it because you're looking for the smallest number of steps. So you can ignore anything that is greater than it. That's what this if statement does. Just hopefully speed it up a little faster. That was the goal. And yeah, the rest is pretty much the same. See, I kept this code here, even though the S bit's not strictly necessary. It still fixes the inputs, right? Because it still changes the S to an A, and you do have to account for the fact that in reality, the position marked S has elevation A, and so that's why I kept this code here, and then just chucked all of the BFS, including the coordinate iteration, up here. But yeah, hopefully that made sense. I don't think it was much of a tough problem, to be honest. Quite easy actually, but also really good, really fun. And this storyline, man, what is this? What's all this stuff about trails and makes no sense. These elves are crazy. But anyway, that was a nice day. Loving the grid graph problem again. Haven't seen one of those this year so far, but now we have day 12. Similar timing to last year actually. I think last year day 12 was also a graph. Yeah, it was also a graph. It wasn't a grid graph, but it was still a graph. But anyway, let's look at the advent calendar and let's see how 24 stars is looking. Still just progressing upwards. I guess we're at the point where the calendar's pretty much the same, so it's not going to be too interesting for a while. More satisfying though. It's like halfway to Christmas now. 48%. It's getting closer and closer. Harder puzzles soon to come. Let's check the leaderboard. Let's see. 740 for the slowest and 3 for the fastest. Yeah. I feel like graph problems can never be solved fast. I say fast, this is obviously still insanely fast, but like never 1 or 2 minutes fast, if you get what I mean. But yeah, these are some awesome times. Part 2, 10 and 4. Yeah, that looks about right, yeah, because I guess part 2 had a longer runtime, at least for me. I don't know, I'll probably work on trying to reduce that runtime. Maybe chuck that in the bonus video for today, I don't know. But yeah, these are some really fast times. Let's look at the stats. Yeah, I mean, day 7, the hard day. I still got a lot of people. Like, it's climbing up, but it's not yet there. It's not yet 100,000. It's climbing up. And yeah, day 12, only 18,000. Yeah, I guess the graph algorithms will throw people off. But also, I mean, it's only like 2 o'clock here. So the puzzle's only been released for, 9 hours? So not long. But yeah, let's look at my school leaderboard. Yeah, a lot of people have already solved today's. Nice. Yeah. Let's check the... an anonymous coming in with those points. Danish missed out today though. Yeah, and cool stole it from him. Part 1 times. Yeah, again, a massive gap between Aiden and everyone else. What on earth was Mr. Will doing? Did he wake up late? There's no way. These people must have woken up late, surely. There's no way it took them over an hour to do today. Nah, can't have. I mean, these delta times are really fast. Anonymous and I've been out for these just over a minute delta times. I think that's faster than me. Yeah, because I just didn't think my program would take that long to run. Oh well, yeah, these are some good times. I don't think Anonymous got onto the global leaderboard though. He just missed out. A couple of minutes. But yeah, that is Advent Code 2022, day 12 done. A graph problem, love the day. I'm sure they're going to start ramping up in difficulty pretty quickly after this. Hope not though. But yeah, we'll see what Eric has in store for us for the next week. Hope you enjoyed today. Hopefully you wrote your own code. As always, you can check out my code in the description down below. There's a GitHub link to my repo. And And yeah, thank you for tuning in, and I'll see you tomorrow.